physicists have long sought to reconcile general relativity and quantum mechanics, two of the most fundamental pillars of modern physics. General relativity, developed by Einstein, explains gravity as the curvature of spacetime caused by massive objects, and it works exceptionally well for describing the large-scale structure of the universe, from galaxies to black holes. On the other hand, quantum mechanics governs the behavior of particles at the smallest scales, revealing the peculiarities of subatomic interactions. However, these two theories, while successful in their domains, are fundamentally incompatible when it comes to extreme conditions such as those found in black holes or during the Big Bang. The search for a theory of quantum gravity, which would unify these two frameworks, is one of the most active areas of theoretical physics. At the core of this quest are phenomena like black holes, which sit at the intersection of both relativity and quantum mechanics. Black holes are regions of spacetime where gravity is so strong that not even light can escape, and their study offers a rare opportunity to test the limits of both theories. While general relativity describes the gravitational behavior of black holes, quantum mechanics might play a role in their inner workings, especially near the singularity at their core. The discovery of quantum effects near a black hole's event horizon, where spacetime is severely distorted, could provide a key to unlocking quantum gravity. Scientists are working on hypotheses about quantum black holes, where the gravitational collapse leads to an ultra-dense point in space. These ideas are still speculative, but the detection of quantum effects near black holes could provide crucial experimental evidence for a unified theory of physics. The tools to study black holes and the quantum universe have evolved dramatically over the years. The launch of the James Webb Space Telescope, JWST, in December 2021 marked a significant milestone in our ability to observe distant regions of space with unprecedented clarity. The JWST is designed to detect infrared light, which allows it to peer through cosmic dust and observe objects that are too faint or distant for previous telescopes like Hubble to detect. One of the telescope's most exciting capabilities is its ability to observe the early universe, taking us back to a time just after the Big Bang. In doing so, it may provide critical insights into the formation of the first galaxies and stars, as well as the growth of supermassive black holes that are found at the centers of galaxies. By using infrared light, the JWST can also observe the environments around black holes with extraordinary precision. As light and matter interact with the strong gravitational fields near black holes, they emit high-energy radiation that can be detected by the telescope. This radiation can tell us about the material falling into a black hole, the behavior of surrounding gas and dust, and the motion of nearby stars. The JWST's sensitivity will also help in mapping the event horizon of black holes, providing new clues about their structure and evolution. Moreover, the telescope's ability to observe distant galaxies will allow scientists to study black holes that formed billions of years ago, offering a glimpse into the early stages of black hole evolution in the universe. The event horizon is one of the most crucial aspects of black hole physics. It is the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. Once something crosses the event horizon, it is lost to the black hole, and all information about its properties appears to be wiped away. This leads to one of the most puzzling questions in physics, the black hole information paradox. According to quantum mechanics, information about a particle's state should never be lost, but the theory of general relativity seems to suggest that information entering a black hole is lost forever. This contradiction lies at the heart of the information paradox, and solving it could lead to a breakthrough in our understanding of the fundamental nature of reality. One theoretical resolution to this paradox is the no-hair theorem, which posits that black holes can be fully characterized by only three measurable properties: mass, electric charge, and angular momentum, spin. This theorem suggests that, once a black hole forms, it loses all the complex information about the matter that created it, reducing it to these three properties. While this simplification makes black holes easier to study, it also raises profound questions about what happens to the information that is thought to be lost in the black hole. The theory seems to imply that once a black hole reaches a certain stage in its evolution, the details about the matter it swallowed are effectively erased. However, this still leaves the question of whether quantum information is truly destroyed, as it might be preserved in some form beyond our current understanding. The process of black hole formation is still a subject of intense study. Most black holes are formed when massive stars exhaust their nuclear fuel and collapse under their own gravity. When a star's internal pressure can no longer support the weight of the overlying layers, it undergoes a violent explosion known as a supernova. If the remaining core of the star is massive enough, it will collapse into a black hole. This process of gravitational collapse is well understood for stellar mass black holes, which typically have masses ranging from a few times the mass of the Sun to several tens of solar masses. However, the formation of more massive black holes, particularly supermassive black holes, is still not completely understood. These black holes can have masses millions or even billions of times that of the Sun, and they are typically found at the centers of galaxies. Theories about their formation range from the idea that they formed from the collapse of massive gas clouds in the early universe to the possibility that they grew through the accretion of matter over billions of years. Studying the formation of these black holes is crucial for understanding the evolution of galaxies, as the growth of supermassive black holes is thought to be intimately connected with the formation of stars and galaxies. While gravitational collapse is the most common way for black holes to form, it is not the only possibility. Some scientists propose that black holes can be formed through other means, such as extreme energy events or the merging of smaller black holes. In the early universe, black holes may have formed differently, possibly from the intense conditions immediately following the Big Bang. These so-called primordial black holes could have formed in the high-density environment of the early universe, when the distribution of matter was highly irregular. These primordial black holes would have different properties compared to black holes formed from stellar collapse, and their existence could help explain some of the mysteries of dark matter in the early universe. In addition to these studies, the detection of gravitational waves has added a new dimension to our understanding of black holes. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as when two black holes merge. In 2015, the LIGO detectors made the groundbreaking discovery of gravitational waves from a B, combined with electromagnetic observations from instruments like the JWST, is transforming our understanding of black holes. With these tools, scientists are learning more about the formation, evolution, and behavior of black holes than ever before. As the sensitivity of these instruments continues to improve, we can expect even more exciting discoveries that will reshape our understanding of the cosmos and the fundamental nature of spacetime. The future of black hole research is undoubtedly bright, with new technologies and techniques pushing the boundaries of what we can observe. The quest to understand black holes is not just about solving the mysteries of these strange objects, it is about gaining insights into the very nature of space, time, and gravity itself. As we continue to refine our theories and build more advanced observational tools, we may soon have answers to some of the most profound questions in physics, such as how black holes form, how they grow, and what happens to information inside them. These discoveries will not only reshape our understanding of black holes but also help us to better comprehend the structure of the universe and the forces that govern it. Cycle 4 million suns, this makes it the exceptional, most recognized article in its ecological components, with consistently more noteworthy exploration on faint openings. What makes these materials so engaging is their multi-layered plan, which has saved researchers expected for a point of fact long-term. These peculiar plans are the bisuggestion, affirmed through mass unusual attributes in atom smasher appraisals. This is fascinating about darkish openings. The most enchanting is their dynamic nature. They don't have clear sizes, and they can hold to widen and not utilize a cutoff point by eating up the including matter. All dim openings get by utilizing consuming gas and buildup found in space, at last achieving there, it is one to astonish. Disablement of the fundamental components capable for the creation of some really tremendous darkish openings. Besides, this cycle has been proposed as one of the expected strategies for the development of focused darkish openings in globular packs. Also, darkish openings can meet with unique articles like stars or great arrangement, other dull openings, to form a giant darkish beginning. Till today, darkish laying out improvement is a subject of checkout. Also, with the leisure activity of James Webb Space Telescope, JWST, we are set to uncover more top-to-rear nuances. Yet, there have been concerns around the risk of a darkish opening blending things up round the town and destroying our planet. Anyway, because of the relentless analysts, these issues have been let pass. They've shown that this current condition can't emerge in all actuality. Expecting that we were to, by certain means, supplant the Sun based with a dark empty of the same mass, the Earth wouldn't be sucked into the event horizon, rather, it would turn around the dark empty, similarly as it orbited around the Sun, based on the equivalent gravitational draw. Also, dark openings don't go through region ingesting glorious our bodies, like stars, planets, or moons. Thus, Earth as a planet wouldn't give up to a dark opening, as none are right up the front inside the area of our planetary contraption. Thus, the solar can't form into a dark empty, since it comes up short at the normal mass to fall inward back to the James Webb Space Telescope. This extraordinary, in Polish, equipment is now not really tough enough to see close by grand items, but it also recognizes substances from the long way off past. The present-day satisfaction is the discovery of around 400 articles in the close-to circle of our planetary gadget that had been previously obscure. This revelation has sent a flood of force through the academic local area, which implies the telescope's enormous effect on how we may decipher the universe. It is critical to recollect that Earth, stars, and cosmic systems are scattered in region, filling very parts, 5% of the universe. This straightforward truth unequivocally recommends that there are several various open doors somewhere within our universe. The James Webb Space Telescope, JWST, is a key impedance, breaking ideal models and opening advantaged understanding every secret and flip. The JWST is the access to a new stage in space research, allowing us to project into the pretentious insider facts and strategies that lie beyond the domain of our creativity. It has not just decided a ton of cryptic objects inside the dull and strange 95% of our universe, but also uncovered the insider facts and procedures of our reality. Boundless circumstances have happened inside the significance of time, but they continue to be hid away in the profundities of the dim universe. Thusly, uncovering the secrets of our universe and its covered-up rules is significant. The JWST is a time machine that licenses us to return to the universe right from irrefutably the principal light to the advancement of cosmic systems through time, as explores happening as surprising. Revelation has changed our cosmic point of view. The telescope found many rarity slices getting back as fast as 600 million years post-Big Bang. This uncommon revelation owes parts to the James Webb Space Telescope's Advanced Deep Extragalactic Study Program, affectionately alluded to as JADES. The JADES program offers the imperative insights for the initial time of huge name and world affiliation, joined with modern age. The JWST, regardless, shapes the way we consider and describe the significance of the universe, uncovering the mysteries and methods locked by existence through space. Scientists spent long time periods accomplishing weary work that included unraveling, examining, and requesting faint, far-off astronomical structures. One of the essential individuals in this work turned into Ryan N., a student from the University of Texas Austin. The great central factor of his studies are frameworks that existed at the start of the universe, around 500 to 800 million years after the start of the huge bang. The specialists known as this time the epoch of reionization. From the test of Ryan and cut off various analysts, clean following the huge bang, the universe was encompassed by a hassle of gas, making it cloudy to vivacious light for such boundless years, roughly 1 billion years post-Big Bang. This haze dissipated, the faint, also, and therefore grandiose straightforwardness, or reionization, began. A seriously enormous amount of specialists conjectured that dynamic, wonderful, large darkish openings or frameworks, turning into an individual from with hot, youthful stars, added to this astonishing length. The JADE programming helped Ryan and his companions in examining those grandiose structures using the JWST's close infrared spectrograph gadget. Their endeavors were designated on sorting out signs of megastar improvement, an excursion that yielded great impacts. Astoundingly, really each universe they contemplated showed genuinely tough outflow line marks, that is a perfect indication of progressing big-name improvement. Ryan's contention is that inestimable blast impacts of the very enormous early sometime of stars had been the fundamental wells for the significant profundity. Furthermore, the research accumulated insights showing that the appearance of stars in these more youthful universes showed an occasion of long styles of wonderful star advancement and short time periods of ionization. While the movement of big-name Earth declined considerably, in light of the fact that there has been a wonderful likelihood that titanic stars could deplete their gas fast and pass roughly detonating in a grandiose blast occasion, they had been generally more than likely chargeable for emptying energy into their conditions, as an outcome obscuring circumstances that could have existed for the fuel to blend to frame new stars. During such quiet lengths, pushing similarly into the story of the making of the universe, Jades acknowledges the lead task via projecting the Webb to catch the early universes, which existed below 400 million years in any event, while the universe turned out to be a still very more youthful global. The significant level norms of the research are the keys to loosening up the privileged insights of how stars molded inside the starter centuries after the huge bang. Regardless of the way that those designs are a large number of light years away, the light coming from them is changed and undergoes changes throughout its grandiose journey inside the expanding universe. Normally, the improvement of the universe broadens the gentle to longer frequencies that appear redder in colors, a characteristic named redshift region. Specialists use the so-called redshift to condemn the whole of universes, and the indistinguishable impact can assist with perceiving those inestimable frameworks that formed at the beginning stages of the universe. Before the technique of the JWST, our discernments were limited to an insufficient few dozen universes with a redshift surpassing 8. A redshift of 8 is a length when the universe was more youthful than 650 million years of age. Anyway, the JADES application has altered our capacities, empowering the identification of, for all intents and purposes, 1,000 of those very far-away universes.